So our next speaker is Simon Dumbill. Simon works at the National Nuclear Laboratory in the electron optics team there, and he's going to be giving us a talk today on chemical mapping with STEM, EDS and EELS, and sort of just discussing the facilities there, I think. Is that fair enough, Simon? Yeah? Great.
It did take a while to load earlier. Okay, good morning everybody. My name is Simon Dumbill. I'm at NNL up at Central Lab in Sellafield. I've been looking at radiation damaged microstructures and chemical mapping of them for just a bit over 35 years now, and have seen a lot of development in the field during that time, mostly around the amounts of data you can acquire. As a quick example, when I first started, we managed to get about 6 months of analytical EDX data onto one floppy disk. That won't even take you anywhere towards gathering a single image these days. Things have changed a lot, and we're all in a really happy place actually. So there's no time like the present. Give you a quick introduction to NNL's capabilities, then a brief overview of why we're doing this. I'm sure you'll know most of that already. And then some highlighted examples taken from the literature covering EDS mapping and EELS mapping to illustrate some of the potential applications and a few of the pitfalls. And at the end, we'll just show the advantages that some good data analysis can bring to an already fairly good data set. So at NNL Sellafield, we've got everything from huge shielded cells that can handle entire fuel elements. In those cells, we typically break the fuel element down into smaller and smaller bits as we apply different techniques to it, and it's possible to, and we can export small sections, even of irradiated fuel from the shielded facility to Central Lab where the electron optics kit is. We also have other Royce-funded pieces of equipment in the facility. There's a Raman microscope and a Raman hardness and optical microscope, which will, in fairly short order, I believe, be installed in the active cells. And on various bits of project work, we have experience covering just about all of the materials involved in the nuclear fuel cycle, graphite, structural materials, fuels, and at the other end, waste forms, and even the detritus left over from reprocessing activities. Just quick go through the specific equipment we've got in Central Lab. Useful for irradiation studies on graphite, particularly. We found the X-ray CT scanner, got a voxel resolution of just under a micron, and has proved fairly useful in monitoring the radiolytic oxidation of graphite. One of the chief assets in the facility has been the gallium fib, which we took active about 5 years ago now, and has done some great work preparing samples we just couldn't access previously. And the key innovation recently has been the acquisition of a cryostage to enable the thinning of zirconium alloys without the fear of putting hydrides into them. Jack showed before an image that was polluted by hydride artifacts from the sample thinning, and when you go to, I say cryo, it's not really true cryo. It's about -100 is good enough, and we're going to be carrying out some experiments during this year to find out whether even -100 is overkill, whether we can get away with not chilling things that far. Depressingly, from a facilities point of view, the manufacturer have told us they're not going to be offering service contracts beyond 2025 on this instrument, which is really quite disappointing, but by the by. The workhorse we've had in place for the last 10 years has been the Joel 2100 TEM, equipped with EDX and EELS, which have enabled the application of chemical mapping in quite a lot of areas for us. Not as powerful an instrument as available nowadays, but it's equipped with a very good X-ray detector with a large solid angle, so we get a fairly decent count rate out of it, and spatial resolution down to a couple of nanometers if you're pushing it. The example at the bottom there shows some EELS studies of oxide metal interface in oxidized zirconium, where each of the phases has a different signature in the EELS spectrum and allows you to map the phases present at the interface. This example was before we had the cryo stage, so unfortunately there's quite a lot of hydriding going on there, which is pure artifact. An example from the 2100 is of some irradiated AGR fuel cladding. This is a 20 chrome, 25 nickel steel. It's seen about 10 dPa, and that's enough for it to grow these large faceted radiation-induced voids, as well as the smaller, more spherical helium bubbles in the microstructure. And the radiation-induced segregation to these features shows up pretty significantly in the nickel silicon maps, and there's depletions of chromium. And as a result of this, we get chromium depletion down to below 10%, which is enough to allow the stuff to etch really differently when prepared electrolytically. And that did cause us quite a lot of problems when we were trying to examine grain boundaries in this material just before the fib arrived, and we found the grain boundaries were etched away and we weren't seeing any chromium depletion because it had all been polished out by the electropolishing. And yeah, there's just an example here of a grain boundary profile down to, like I say, those 10% sort of numbers. And the map also shows the different spatial distribution of silicon there, so we can tell that we've got nickel 3 silicide precipitation at pre-existing dislocation loops, and also just nickel segregating rather more diffusely to those areas as well. We've recently acquired a plasma fib, which also has a SIMS detector on it here, so we can collect the sputtered ions that the fib creates and analyze those. Haven't got any really great applications examples from that yet, but watch this space over coming years. And we are in the process of installing an aberration corrected Joel 200F, which next time the engineer comes, we hope to get some electrons down it, at which point we look forward to some higher spatial resolution, analytical capability, and much higher throughput compared to the 2100. When we were out getting the demonstration on the Joel, we took with us a waste form sample where originally it had been believed this was a glass, but we found these crystalline areas in it. We're able to produce these atomically resolved EDX maps showing the co-location of calcium and moly in the crystal structure in that. The right-hand example there is a grain boundary in stainless steel, which we mapped with EELS, and the results there are on the right-hand side, although there's no vertical scale, shows you that the moly and the boron are enriched at those grain boundaries, very much the same spatial distribution. We'd taken that same sample to demo on a previous generation of FEG-TEMs 15 years previously, and it took us an entire morning to get an analysis the same as we managed in 3 or 4 minutes on the new instrument. So, well, I've already kind of spoiled some of this slide. Why are we doing this? We're doing it because the damaged microstructures, I mean, Jack illustrated what those look like, but in irradiated materials, the defect flows that produce those structural defects also produce chemical changes over the distance, typically only of a few nanometers, although those at higher temperatures, those diffusion fields are somewhat larger. So as well as knowing what your material looks like, if you want to understand how it's going to perform, if corrosion is a concern, for instance, or if phase stability is likely to be threatened by irradiation, then you've got to do chemical mapping or some kind of microchemical analysis to find out how the material is performing. And I've very quickly gone through some examples from our own work, and now she'll take a bit more time to use some examples from the literature. In fact, there's even some examples from various my colleagues here in the room today. So let's have a look at that. On EDS, first of all, this is what happens in your microscope. The beam comes in from the top, interacts with the sample. We produce X-rays, backscattered electrons, photons. We get elastic scattering, which gives us allows us to use imaging, like Jack was showing, and the inelastic scattering informs us also through the Eels technique. So let's look at what happens with X-rays. Here's an example of an X-ray spectrum, and the things that, obviously, it's a statistical process, is turning that into some meaningful compositional data. So things which will help us there are having a lot of counts in the spectrum, and in that case having a field emission gun. TEM is enormously advantageous. Aberration correction adds another factor of 3 to 5 to the beam current that you can get into a small spot, so that is also a huge advantage. And high solid angle, high collection efficiency of those X-rays is obviously vital. Modern high-end analytical detectors for TEMs tend to be about 1 steradian in collection angle. I think the most that is currently offered is an FEI machine, which is claiming to offer 4 steradians of detection, which is crazy. I mean, that's most of the sky covered with a detector, and is an enormous step up from where things were. When I first started using EDS, a big detector was about 0.15 steradians. So we're collecting a lot more data. We can do a lot more with it these days. With high detection areas comes other problems which are more or less well corrected depending on the software that you're using and the manufacturer of the gear. Pulse pileup becomes an issue. You end up with doubling peaks. So the oxygen peak here is huge, as is the aluminium peak. If you're counting quicker than the electronics can cope with, you'll end up with smaller doubling peaks here where 2 coincident photons have not been separated properly by the detection system. And that's still a feature. I mean, despite the advances in electronics and online processing, if you haven't got the pulse pileup correction switched on, you will be seeing those peaks really prominently. And even if you have, sometimes it doesn't do a great job if the count rates are too high. It's not terribly likely in TEMs, but certainly SEM applications, it's a pretty big problem. Other artifacts that you need to be aware of are particularly from sample activity. If you're using an electropolished disc, there's a huge amount of the disc which you're not using but is contributing radioactivity to the background signal that your X-ray detector sees, and that can require some substantial corrections to try and remove artifact peaks from. In the case of neutron irradiated samples, it results in a very large manganese, or apparent manganese X-ray peak, which, since it sits right here on the back end of the smaller chromium peak and overlaps with the iron peak, has to be accurately deconvoluted, or attempted to anyway, otherwise the quantification is going to be completely meaningless. To get decent analyses out of a grain boundary, it's not just enough to find a grain boundary. You've got to make sure that it is really well aligned with the beam. If the boundary is twisted, as it inevitably will be if you're going to map a large area, the effect of segregation to the boundary will be diluted in the projected image that you finally see. So making sure that the boundary is properly aligned to the beam is pretty essential. For EDX, you can definitely have samples that are too thin. You just don't end up with a lot of counts coming out of them. And too thick results in too much beam spreading within the sample. And that will degrade your spatial resolution. Sample cleanliness is a bit of a touchy subject. With electropolished samples, it's essential to plasma clean them to get rid of any hydrocarbon contamination on the surface, because that will migrate to the beam and just result in a filthy black mess that you can't see through. Samples can be too clean though, and if they're extremely clean, you end up just drilling holes in them when you keep the beam stationary on the sample for too long. Taking account of all those effects, at the end of the day, as I said, it's a statistical process, and there are trade-offs that you can employ depending what you want to get out of your data. Forgot where I was going with that. The trade-off really is about acquisition time. Slides are out of order. Let's go on to some examples here and kind of illustrate the point. These are some maps taken from by one of a student I was industrial supervisor for here at Manchester, Chiara, a few years ago on 2025 fuel cladding, and she was mapping the grain boundaries here to look for segregation of the major elements. And you can see that the images were a lot clearer originally. They hopefully will be in the versions you'll get. This boundary here, for instance, is pretty well aligned at this point, but gets broader at the top, and I'm not quite sure what happens to it down here. You can see that there's also segregation of nickel and silicon, particularly to defects within the matrix either side of the grain boundary. And because this has been, I think this was a 128 pixel square map, even though a half an hour acquisition means that there's a reasonable amount of noise and scatter in these plots. And the choice there, I guess, is that if you want accurate quantification of what's at the grain boundary, then maybe mapping isn't the thing, or maybe you need to map over a much reduced area, something to get more counts into those spectra. You can produce what looks like a really plausible map, and then you extract the individual spectrum that underlies each of those points, and you'll find there's only a remarkably small number of counts in it, and certainly nothing that would bear any form of statistical analysis. A further example of that is one of the samples we'd looked at. This is a neutron irradiated sample, and was indeed one of those cases where we had to do quite a bit of work with the EDX processing to remove the radioactive component from the data. And this is our Lab 6 microscope, so the count rates are rather less than they were in the FEG that Chiara had been using, but we can still see the differences, well, the fluctuations in the concentration of nickel and chromium and silicon there. And we've got a really very good measurement of the depletion and enrichment profiles here, because these were taken using single point analyses where each of these was maybe 30 seconds of data acquisition time. So the error bars are much smaller. This is an example from Alex's thesis, where the figure at the bottom here, and this is what I was alluding to about, do we want illustrative data or quantitative data out of our maps? And the spreadsheet at the top there just runs through a really basic sort of calculation on how many X-rays you're going to get into a pixel in a given amount of time. And the figure at the bottom illustrates that really nicely in terms of the uncertainty in the quantitative composition. So if you start off with a low number of counts per pixel, then the spread in the quantification is enormous, whereas when you increase the dwell time up to something much more, producing a much better spectrum, you narrow the error bars, and the distribution of measurements comes right down. So it just illustrates the importance of spending long enough doing the mapping. But that might mean you get 4 or 5 maps done in a day, which might not feel like a lot of work compared to the number of images you could produce if you were doing dislocation imaging or something. And this is illustrated again in an example of an irradiated weld in type 304 steel, where the map that had been produced here does a good job of illustrating the clustering in the matrix and some segregation to the grain boundary, the presence of some irradiation-induced phases in the other grain. But when you start extracting data from the map and displaying it as a line scan, you get an illustration of what's going on, but the noise levels are still pretty significant, and would be better illustrated with either a straight one-dimensional line scan or or a much smaller map. And this example goes back a long time to 1989 from some of my colleagues at Harwell, when we were using the old vacuum generators stem that we had, which would produce about 1 nanoamp into more or less a 1 nanometer probe. In terms of the electron optics of the system, it was brilliant for the day. The X-ray detector, however, was pretty tiny, as you can see. And to acquire the data, this data set would have been an array of maybe a dozen static points across a grain boundary. And the result of that is that we can see there's very good, very smooth analysis of the compositional profile at the grain boundary, which is able to be quantified to show how much phosphorus was there in terms of phosphorus coverage of a single plane of atoms at the grain boundary. And if you're after that kind of measurement, you've really got to spend the time acquiring the data. Mapping will show you what's there, but you will not measure things unless you've got enough counts present. This is an example from a paper by Alan and other co-workers here at Manchester a little while ago, when the chemist was still fairly new. irradiated zirconium. We're looking at the dissolution of a second phase precipitate in the zirconium here. So the precipitate sort of originally inhabited this kind of volume, and with the progressive irradiation, it's built up rafts of dislocation loops on the basal planes, and you can just about see it. It's the horrendous pixelation on this. The iron which has dissolved out of the SPP reprecipitates on these loops, and you can see that in a halo effect around the original SPP. I think chrome appears to do the same thing. You can see these lines of enriched chromium, and I can't remember the story now, but I think the tin is enriched between the loops, isn't it? Shown in the map on the top right there. And this is a really good example of the illustrative power of mapping. Doing something like this with point analyses, it doesn't have the same impact at all. This is another EDX example from Alex's work on irradiated pressure vessel steels. So this one was proton irradiated at DCF, and then has been analysed in the Talos microscope here. And in completely different ferritic steel, we've got segregation of nickel to the grain boundaries, really nicely illustrated here. And you can see this section of the grain boundary is really quite well aligned, and it gets much broader here as it goes around the corner. Which brings me to one of my areas of doubt on radiation-induced segregation. There's quite a lot of effort is expended on mapping grain orientations and trying to correlate different grain boundary characters with different quantities of segregation. It's just not that simple, because all you've got to do is look at any grain boundary in an image like that, and you realise that it's different along its entire length. There's no such thing as a particular orientation for that grain boundary. It's just different everywhere. And I think the best you can ever do really is to analyse a number of grain boundaries, if that's your thing, and try and see what the spread of segregation values is. In my experience, it's not that great, except obviously if you're looking at something daft like a twin, which isn't a grain boundary anyway, and you should be able to spot that. Alex also did some really great mapping on these radiation-induced clusters, which tend towards two sorts of types really. There's the manganese nickel silicon G phase, which is a late blooming phase at high doses in irradiated pressure vessel steels, and also to the nickel segregation to dislocation loops in these two locations here. And the spatial resolution in these maps is really excellent. Okay, sorry, just nip back to the slide I had on the eels overview. So, as the electron beam passes through a sample, it loses energy. EELS analyzes the energy which has been transmitted through the sample. We have an intense peak in the spectrum where no energy has been lost. In the low loss region here, we get plasmons which are related to the energy loss of the electron as it goes through the sample. Measuring those plasmons allows us, or measuring the intensity in the plasmons allows us to measure thickness, as we've already heard. And the shape of those plasmons can inform us on which phases are present, or at least their distribution. It's kind of difficult but possible to model the plasmon shapes for different phases. If you're looking at oxide metal interfaces, it's quite easy because the oxide plasmons are usually very distinctive, as we saw in the example right at the beginning. There are also characteristic ionization edges due to each of the elements. The light element ionization edges unfortunately fall in this low energy region where the signal is really intense and varies very rapidly as well. But it does at least mean that we can potentially map all elements using eels. With EDX, there's an effective cutoff. Carbon, boron's about the limit. Lithium, the EDX manufacturers claim they can distinguish lithium, but only when there's lots of it there. It's fine for battery materials and stuff of that sort, but if you're looking for transmuted lithium, for instance, probably not enough of that there to detect. And all of these features can be used in eels for mapping. One excellent advantage of eels is that it is insensitive to radiation from the sample. So you can be using an electropolished sample and won't see any degradation because of sample activity. The downsides are that absolute quantification is possible, but it's a lot more difficult than it is with EDS. And one of the reasons for that is because, as I said, the intensity of the background regions where these ionization edges occur varies by orders of magnitude amongst the different elements. So the useful edges that you might want to be looking at could be at a much higher energy and will require either a separate acquisition or a much, much longer dwell time to get the statistics up in the spectrum. In EDS, it's a lot simpler. So this is an example, it's not a nuclear example, unfortunately. It's from helium-implanted silicon, but it shows, all right, here we are, silicon, the plasmon's at 15 eV, but the helium ionization edge is quite distinct from it. And that allows you to produce a map like this, which shows that only these two bubbles out of this chain of 7 have actually got any helium left in them. The others must have intersected the surface of the sample and just become punctured during the course of the sample preparation. And the other thing that it shows and that you can use is there's a surface plasmon which is specific to the bubble to matrix interface. So it shows you that they are they're proper cavities. Another example of the gas bubbles is in this one from some of our colleagues at Glasgow, who were looking at xenon implanted zirconium. The xenon edge is in quite a high energy loss range, but and in the, hold on, where are we? They were using shape fitting essentially to extract the xenon intensities, and turns out that if you just use the contrast that's available in STEM, because of the thickness variation through the sample, the local intensity rises where there's a bubble were really quite difficult to see. So they fitted the background shapes due to the matrix, and were able to extract from that a good map there for the xenon bubbles. And yeah, those are 2 to 3 nanometer scale bubbles mapped with pretty good resolution, so you're able to determine their size quite well. This is a rather more detailed piece of work, similar to the image I showed at the beginning. So we've got here the characteristic shapes of the plasmons for the phases which are present around the interface of some oxidized zirconium. As I said at the beginning, the hydrides are present in this image and really quite distinctive, but are mostly artifact due to the fib preparation. The other interesting feature is that this technique is probably the best there is for really showing quite clearly the suboxide phase, which is present at the oxide metal interface. And it was also possible to extract the oxygen concentration profile as you come in from the oxide through the suboxide and then through a decaying diffusion profile of oxygen into the metal. Trying to do quantification like that of oxygen with EDS is perilous. It's much more difficult to do. This light elements are quantification of light elements is one of the areas where EELS really wins out. So this example shows the examples we've seen so far with EELS have been point-wise analysis. So you take a spectrum at each pixel and perform data processing to reveal the information present in the maps. This example uses the EELS spectrometer as an energy filter on an image. So you acquire an entire image at once, and by acquiring images, let's say at this energy loss and this energy loss, you can extrapolate the intensity under an image. If you take another image directly under one of the ionization edges, you extrapolate the intensity from that and you're left with essentially an element map. And that's been done in this case for iron, chrome and nickel in this irradiated stainless steel. It's showing the enrichment of nickel and the consequent depletion of chromium and iron around radiation-induced voids and dislocation loops. Now, this is the same sort of data we saw earlier on, acquired with EDX on the irradiated AGR fuel cladding, but illustrates that because the ionization edges for the different elements are scattered across such a wide energy range in EELS, they weren't able to carry out the analysis for silicon using this method, or at least not in the same data set. A separate, totally separate data set would have been needed to do that. One of the other perennial problems with EELS and looking at structural materials is the fact that the relative intensity of these edges also changes. And nickel is a particularly inefficiently excited edge. And consequently, despite the fact there's 10% nickel present in this steel, that's a miserably unimpressive edge. This is another example from using F10 energy filtered imaging, acquired using an instrument down at Oxford to map yttrium or yttria precipitates in a steel. And here we've got really quite small precipitates, visible yttrium precipitates, and it's also, I'm not sure whether you can see it, but there is a correlation with chromium in there as well. So they're yttrium chromium oxides. And in this case, they'd chosen quite a low energy loss for the yttrium edge, which wouldn't normally be used, but by using some good data fitting techniques, they were able to unscramble the presence of the nearby plasmon energy and produce some really impressive images for yttrium there. Yttrium's quite, in other systems, yttrium can be quite difficult because it overlaps with other elements, so that's why this particular paper was on my radar. And finally, we come on to data processing. Because the analysis to turn these maps into, or to extract signals from these maps as a statistical one, then statistical analysis techniques are very useful in improving the data and bringing out correlations that maybe aren't obvious to the eye. So there's multivariate statistical analyses or principal components analyses are two of the common approaches that are employed. There are plugins available for most of the available image processing packages that are commonly used. So Digital Micrograph, HyperSpy, ImageJ, they've all got readily accessible and usable plugins. And this example shows really very well just what sort of enhancement this kind of processing can make in all of the elements here. The definition in the processed images on the right hand side is just enormously improved, and it gives you the equivalent to acquiring your data about 5 times as long, it looks like, on that basis to me. And will bring out correlations that the next example will illustrate. In this particular case, we've got, this is another pressure vessel steel, I think. So the irradiation has produced more of these fine-scale manganese nickel precipitates, which are, when the principal components analysis breaks down the potential contributions to a spectrum. So this will be kind of the average, and then each of these is a different phase contribution to the eventual experimental spectrum. So one of them is a vanadium and chromium precipitate. One of the components has just manganese and nickel in it, and there's another one containing the oxygen signal. So the apparent visibility of these separate components can be revealed by the statistical analysis process as well. This is just a list for your perusal afterwards of the examples that I've used. And I think this is the final thought. This was a little phrase that I came across. My wife is busy learning jazz at the moment, and the process of learning was thought to be something like imitate. So find something you really want to play and learn to copy it, then assimilate, learn how that copying, how the original was composed, and then take it on and innovate, do your own thing. And I hope what I've given you here is some examples to imitate, and further reading in the literature will allow you to assimilate the information, and then I'll leave it up to you to figure out how to use it. So thank you.